Now you can see what I'm sharing, yeah?
Yes, we can see it.
Okay, thank you. I just want to see whether you can move up and down. That is okay. Now, so we continue with our discussion on that is complex multiplication method for constructing elliptic curves. We had looked at several concepts on how to generate, construct elliptic curves, and of course, that is what we want to go deeper inside. So far, we know several properties of elliptic curves, including their orders, prime factors, and embedding degree, and even the base field, the field in which the elliptic curve is in. So these are the properties that we then consider when we are constructing an elliptic curve. So to construct elliptic curves, just to recap what we did, one, you have to identify the field in which you want your elliptic curve to be in. Let's say FQ. Then you must decide how many points you want your elliptic curve to have. So the order of the elliptic curve. So this is the number of points that this elliptic curve would then have when defined on this field. Now, once you have that, let's just say maybe you want your elliptic curve to have 20 points. And let's say that you want it to be on the field F13. Just for example's sake. Now, once you've done that, you would then calculate the trace. And the trace is calculated such that the number of points will be equal to the base of the field. That is the field is the best field is mod 13. Then plus 1 minus t. So this is how you trace. Oh, thank you. So I was just recapping what we had already done in the previous days, and yesterday also, what we did. So partly I was going through the steps for constructing elliptic curves. And the first step, as we've seen before, is to choose your field, the best field that you want your elliptic curve to be in, and then decide how many points you want, the order, number of points. So decide how many points you want, your elliptic curve to have. So once you have the number of points, let me say that 20, and let me say that your field you want it to be in F13, then you would now calculate your T, the trace. Once you calculate the trace, you will proceed and get the complex multiplication discriminant. And that's what we saw yesterday and the day before. That the discriminant D, after you've chosen your field and Q, and then the field, and then the number of points that you want, and then you have your T, you proceed and find the discriminant. And there are some properties that the discriminant must meet. And one of the properties that the discriminant should be less than 0. And the other one is that the discriminant should be congruent to 0 mod 4. If this is not the case, then it should be congruent to 1 mod 4. If it's not congruent to 1, it must be congruent to 0. And the other property that the discriminant must meet is that 4 multiplied by Q, the Q you chose in your field, 4 multiplied by this Q should be congruent to T square. Remember, we just calculated T here from this step. We just calculated T. So congruent to T square plus the modulus of T by B square. Let's continue. Now, so I think that is enough about the recap of what we've been doing. So our today's focus would then be to look at the role of this complex multiplication discriminant, which I've just showed. I've told you how we will then be getting it. So then we'll be looking at its role in calculating or constructing an elliptic curve. Then we shall be seeing how to compute the Hilbert class polynomial. And then after computing the Hilbert class polynomial, we shall be seeing how to project it onto the field that we chose at the beginning. And then from there, we shall be seeing how then we choose an appropriate curve equation for it, depending on the J invariant that we obtain. Then, of course, we'll be seeing how to come up then with the code for getting the J invariant. So these are the three things I want us to look at how we get them. So to do that, we'll be using an example. So let's pick this example just to explain our concepts. This is slightly different in some aspects from the one we did yesterday and the previous day. And we'll be seeing at where the difference comes in. Now, so we are given the elliptic curve. We know this elliptic curve is y square is 8x. No. Y square is x cubed plus 8x plus 8. But we want to assume we don't know this curve, because this is what we want to come up with. We want to do our calculations and then come up with this thing. But now, so what we want from the start, we assume we don't know this because this is what we want to get, but we know it has 20 points. So we want to come up with an elliptic curve that has 20 points, and we want it on the field F13. So we want this elliptic curve, we want to try and construct, and we want to see whether we can, in the process of constructing, whether we can come up with this equation. So to begin with, since we don't know the curve we want, we only know the property that it must have 20 points and it must be on F13. The first step, we say we calculate the trace. So the trace will be the number of points is equals to the field, the base of the field, plus 1 minus t. And this is 14, goes to the other side, it will be 20 minus 14 is minus t. So that minus t becomes 6, and t becomes negative 6 when you do that. So we have our t. It appears this network today is so poor. Now, so the discriminant must be less than 0. And then the discriminant again must be equivalent to or congruent to 0 mod 4. If this is not the case, then it must be congruent to 1 mod 4. One of these cases must be correct. And then the other property is that 4 multiplied by q that we chose should equal to, or should be congruent, let me just say congruent to t square plus the discriminant, the absolute value of the discriminant multiplied by b square. Now it is absolute value because you can see our discriminant is less than 0, so it's negative. So when we take the absolute, it means we are only considering it as positive. Now, so normally we don't actually use this one so much. We use this one just at the last end to ensure that it meets these conditions. But the one that is normally used to find a D is this. So after finding D using this condition, is when you can maybe want to see whether it also meets these other three conditions. So that is the one I've used. Our Q, we've chosen 13. And our T, we've found -6. So when you multiply this is 52, and this is 36. So doing this, if 32 crosses the equal sign, we would have 16. So this is what you end up with. Now, at that point, now you have to think, what becomes of D? What should be our D and what should be our V square? Also, you have 16 is equals to two things multiplied together. So 16, from here we can see 16 equals to D multiplied by square of V. So what are the possibilities? What are the possibilities? The possibilities of getting 16 as a product of two numbers. One of the possibilities that we can have 16 times 1. We can also have 16, we can have 8 times 2. We can have 4 times 4. These are the three possibilities of having 16 written as a product of two numbers. Now, so you can see that this one, of course, is not correct. This one will not give us b square, because none of these two numbers, 8 and 2, none of them has a square root. None of them has a square root, because we want one that has a square root, so that we get v. Because v square is one of these two numbers, but none of them is a square root. It can give us a square root. So it then means that we have these two possibilities. The possibilities could be that 16 could be D, and V square could be 1, if you consider the first possibility, which then means that V is plus or minus 1, the square root of 1, plus or minus 1, which is the square root of 1. The other possibility is that D could be 4, and V square could also be 4. And if V square is 4, then it means that V is just plus or minus 2. Now, then you must now consider the other conditions. The other condition for D was supposed to be less than 0. Was supposed to be less than 0, but you can see here, we have said D is 16. So that means, oh, it's not even D. It's supposed to be absolute value. The absolute value of D is 16. It's supposed to be absolute value because of this. It's supposed to be absolute value of D is 16. So that means, therefore, D itself is negative 16 because it's supposed to be less than 0. D is negative 16. When V is plus or minus 1. And the other possibility here, we had seen that the absolute value of D is 4. So that then means that D itself is negative 4. D itself is negative 4 when V is plus or minus 2. So that is how you come up with the D and come up with the V. And this is the second step, because the first step was just choosing your field and declaring how many points you want. So for this question, we declare we want 20 points, and the field we want F13. And so we calculated T, and then we've now found D, where T was the trace and D is the discriminant. Now, so after finding that, the discriminant, we now want to get the Hilbert space polynomial. The Hilbert space polynomial, of course, so this is what I said, that is our D and V. Now we want to get our Hilbert space polynomial. But to get the Hilbert space polynomial, we must get the set of ABC, the set comprising of integers ABC. Integers are just whole numbers, whether negative or positive whole numbers. So we want to get a set of integers ABC. And this set of integers ABC is what will help us get the Hilbert space polynomial. Now, how do you obtain this? Again, we have some conditions. The first condition is that the D we just obtained above, which could be -4, -16, that D should be written as B square minus 4AC. And the other condition is that A must be less than or equal to the square root of the discriminant divided by 3. And it should be greater than or equal to B. And the other condition is that this A must be less than or equal to C. And these are not the only conditions. The other condition is that if B happens to be less than 0, then its magnitude, its modulus must be less than A. Must be less than A. If it happens to be 0. Remember, at this point, it was less than or equal to. But this is a point when it was not less than 0. But if it happens to be less than 0, then this must be obeyed. So these are the conditions we will now be using. Now, so if you're writing your code, how does your code then get this? How does your code get A? How does it get B? How does it get C? How does your code do this? So your code, you write it such that it can first of all compute this. It can first of all compute the maximum A. Maximum A. And first of all, obtain the maximum A. So once you obtain maximum A, let your code know that A is supposed to be positive. I was explaining how you then write your code that will give you the set ABC. How you would then write the code that will give you ABC. I was saying that your code must, first of all, must find a maximum. And that's what we'll be doing. A maximum is the discriminant, the square root of the discriminant out of 3. Supposing a maximum is 2, then the code is supposed to loop through all the points between 0 and 2, inclusive, to find out which one is A. It's likely that not all these will be A. Maybe one of them or 2 of them will be A. So it will then loop through to find out which one is the correct A to be used. Now, after finding A, it will then find B. And B is supposed to lie between A and negative A. So that means after looping through all the values meant for A, we'll again loop through all the values to find out which one is B. From negative A to positive A, it's supposed to determine 1B. And to determine that, it's supposed to use this equation. Because you now have A, so you try the first option for B and see whether you can obtain C. If you cannot, try the second option for B and see whether you can obtain C, and so on. So let's do this example. Let's just do this example. Of course, that is how your code will be working. The way we're just working is how the code will then be working. Now, I want to determine, we will just determine D and V. So our next task is to determine ABC. And the first thing we do is to determine the maximum A. Maximum A. So I first of all chose on this. I'll then come to this later. So I wanted to begin with this to determine maximum A. So maximum the square root of D out of 3. Absolute value of D is negative 16. So its absolute value would then be 16 divided by 3. The square root is approximately 2.31. So that means if this is the maximum value, it means A is less than or equal to this. So, and A must be positive, as I said. So A is likely to be 0, A is likely to be 1, A is likely to be 2. But it cannot be 2.31 because 2.31 is not an integer. A is supposed to be an integer. So the only integers in the range 0 to 2.3, the only integers are 0, 1, and 2. So A is any of these. It could be 2 of them, it could be all of them, or it could be 1 of them. So we just want to check to see which one of them is A. So how do we choose? How do we then determine? We determine, what will help us determine is when we proceed and try and see whether we can obtain B. We try and see whether we can obtain B using the A we have. The one that gives us B is a correct A. The one that does not, we leave it. So let's try. So that is what the code will then be doing. The code has these 3 options. It wants to determine which one will be A, which one will be A. So it then knows that there are other conditions that B must be in the range of A. No, B must be less than or equal to A, and which must, this one we've already used it. This one you've already used it. Okay. And the other one is that B must be less than or equal to A. B must be less than or equal to A. And the other one is that B must be in the range of negative A B must be in this range. Now, so let's assume that A is 0. And we want to see whether we can get B. We want to assume that A is 0. So if A is 0, then it means B must be in the range. I'm using this. If A is 0, if A is 0, A is 0, that means B will be 0. It means B will be 0, but let's see whether that is possible. Let us see whether it's possible that B will be 0. So then we come here. Come to the next condition. The next condition which says, now if B is 0, can you get C? It will be 16. If 16 is equals to 0 square minus 4A is 0, C. So it means we cannot get C. We cannot get C because negative 16 is equals to 0C. So we cannot get C. So since we cannot get C, it means A cannot be 0. Because if A is 0, it has forced B to be 0 using this range. Because B must be in the range negative A to A. But A is 0, so it means B is also 0. And if B is 0 and A is 0, we are unable to get C. So it means A cannot be 0. So we've disqualified 0 from being an option. Let's proceed and check whether A can be 1. And that's what the code will be doing, because I said the code will be looping through all these values and checking which one is possible to be A. Let's consider 1 and see whether A can be 1. What will happen to B? B is supposed to be in the range negative 1 to positive 1. So if B is in that range, so it means B is likely to be 0. No, it's likely to be negative 1. It's likely to be 0. It's likely to be 1. Okay? It's likely any of these three. Now let us see whether any of them will work. If any of them works such that we can get C, then we take A to be 1, and we take B to be that value that has worked. We come back to this equation. I want to consider negative 1. I want to see whether if B is negative 1, I can get C. So negative 16 is negative 1 square, which is 1, minus 4, and A is 1, multiplied by C. This one coming this side, I would have negative 17 is negative 4C, which means 4C is 17, or C is 17 out of 4. 17 out of 4 is not an integer. It's not an integer. So that means B cannot be negative 1. B cannot be negative 1. Let's try and see whether B can be 0. So that is what the looping means. You're looping through all those possibilities. You want to see which one then becomes 0, if any of them would become. Now, assume B, there's a condition that says that if B is 0, then now if B is 0, not 0, not 0. The condition talks about if B is negative. If B is negative, not if B is 0. Now, so if B is 0, so we just come back here. Just come back and see whether you can get C. B is 0. Just come back here. Negative 16 is 0 square minus 4. Our A is 1, multiplied by C. So negative 16 is negative 4C, which means 4C is 16, or C is 4. So we found that it's true. It's true that A can be 1 and then B be 0. A can be 1 and B be 0, and in that case, C will be 4. So that is one scenario. A is 1, B is 0, C is 4. Let us check whether it's possible, because we are checking which values of B are correct. We say that out of these 3, all of them could be correct, or one of them or 2 of them could be correct. So we just found that negative 1 is not correct, but 0 is correct. So let's find out about 1, whether 1 is correct, because 1 was the other possibility. So we again come here. Negative 16 is 1 square minus 4 AC. A is 1. So this is positive coming this side to the same case we had earlier, is negative 4C, so that C is not an integer. C is not an integer. So we've confirmed that the only value that B can take is 0. The only value that B can take is 0. Good. That is, if we take our discriminant to be negative 16, if we take our discriminant to be negative 16, we come up with this set. Now we had another option that our discriminant will also be negative 4. So we find maximum A. Find maximum A. Maximum A will be 4 out of 3. So this looks like 1 point something. 4 out of 3, the square root of that should be 1 point something. So that means our maximum A this time is 1 point something. So that means since our A is supposed to be positive, it can only be 0 or 1. One of these, 0 or 1. When the discriminant is 4. So again, we check which one is A, which one. So we look through all these values. We look through 0, we look through 1. We want to see which one would then be A. Let's consider 0. Let's begin by considering 0 because it's the first element we have here. Just as we reasoned earlier, we know that B must be in the range negative A to A. Negative A to A. So when A is 0, it means B is 0. So that it's in this range. B must be 0. Now, is it true that B is 0? Let's now go to this equation and find out what will happen? Can we find C? Now, if you put B to be 0, put A to be 0, so you find that negative 16 will be 0 minus 0C. So you cannot get C. So that again disqualifies A from being 0 this time again. So you are left with one option, consider A to be 1. Consider A to be 1. If A were to be 1, oh, this one is not supposed to be negative 6, it's supposed to be negative 4. It's supposed to be negative 4 is equals to B square minus 4AC, because we already done with considering D to be negative 16. So this time you're considering D to be 4 negative. So if A is 1, what is B likely to be? What is B likely to be if A is 1? B is supposed to be in the range negative 1 to 1. If A is 1, B is supposed to be in this range. So that means B is supposed to be negative 1, 0, or 1s. Any of these, or two of these, or even all of them, but we have to consider each one of them to see whether it will be correct. So if A is 1, B is either all of this, or two of this, or one of this. Let's see which one is it. Let's take negative 1. And this is the equation we are now using. Let's take negative 1. So negative 4 will be negative 1 square, which is 1, minus 4C, because A is 1. So this one crossing the other side, you have negative 5 is negative 4C. This means that C will not be an integer. C will not be an integer because it's 5 out of 4. So that then means that when A is 1, B can never be negative 1. B can never be negative 1. What about 0? Can it be 0 just using the same equation? Just using the same equation. Put where there is B, put 0. So this point becomes 0. This point becomes 0. So that means we have negative 4. Negative 4 is equals to 4C, or C is 1. Or C is 1. Yes. So that means we have found a possibility. Another possibility is that A can be 1. And if that is the case, B will be 0. And then C will be 1. So this is another possibility of the set ABC. Let's finish by checking whether B can also be 1. We want to check if B can be 1, again, using the same equation. So all these calculations, I've done them, but I just want us to calculate from here. Then after that, I'll show you the calculations. Let's consider B as 1. So that would be negative 4, 1 square minus 4C, minus 4C. This crossing will be negative 5 is negative 4C, or C will be 5 out of 4, which is not an integer. And therefore, B can never be 1. So B is only 0. And these are our two scenarios. These are our two scenarios. Now, so we now have our sets ABC. What follows is to calculate the Hilbert space polynomial. So let's just move with our notes so that we now follow the notes. We have obtained our two sets. That means the Hilbert space polynomial, we would get it. But before that, we have to get J invariant. And every set will have us get a J invariant on respect that is for that set. So every set will have its own J invariant. That's what I mean. Okay. I think there's something, I don't know whether you consider this, we did not consider this two as being A because I'm seeing some different result here. We only have this. I don't think we consider this two when we are considering still just on when D is negative 14. When D is negative 14, because we had said that the maximum value A will be this. That means A is supposed to be positive, 0, 1, or 2. So we had considered this and that. So let's consider 2 and see what happens. I think we considered 1 twice instead of considering. So now B will be in the range. B will be in the range negative B, which is negative 2 to positive 2. B will be in that range. So in fact, this range means negative 2, negative 1, 0, 1, and 2. So one of these, or you continue, you disqualify using this equation, and disqualify using this equation at every point. For instance, consider being negative 2. So if B is negative 2, this would be negative 16 is equals to 4 minus A is 2. A is 2. So 4 times 2 will be 8. This one, go the other side will be negative 20. Negative 20 will be less than or equal to negative 8. So that means you have C as negative 20 out of negative 8, which will not be a whole number. You will also consider this, you will disqualify it. Let's consider 0. Remember that our A is 2 this time, and this is, we're considering B to be 0. So that would be negative 16 is 0 square, which is 0, minus A is 2, that would be 8C. So this is negative 8C, would be 16 negative. So C will be 2. C will be 2. So I think while we were doing, we forgot to consider 2. I think, I don't know what we considered. We might have considered 1 twice. And that is why we did not see that there was this other set. Now, so when D is 16, when D is 16 negative, we have these two. We have these two values of ABC, sets ABC. So we proceed with them to find our J invariant. And the J invariant, the formula is X minus j into the discriminant, the modulus of the discriminant out of the usual out of measurement. This one I used a shortcut, but it's supposed to be negative b plus square root of d out of 2a. Out of 2a. This is a formula we used yesterday. So in our case, in the first case, b is 0. B is 0. So if b is 0, this value disappears. This part disappears. And that's why you can see I only have the square root of negative 16 out of 2a, and our a in this case is 1. So this one is already summarized. But then the formula is this. This is the formula. X minus j into negative b plus the square root of d out of 2a. So this is the formula you put in your code if you are writing the code. Now, when b is 0, then this point disappears. So you're only left with the x minus j into the square root of d out of 2. But how does I come in? I already explained that yesterday, that the square root, we cannot get the square root of negative 16. Just like that, because this is a complex number. So the way we do this, we take it as negative 16, now 16 times negative 1. But then we know that this can be written as root 16 times root negative 1. But root negative 1 is a complex number. The answer is I. So that means this is root 16 times I. That's why we arrive at this point. Now, so in the first case, our a is 1, so the denominator is 2 times a. So 2 times 1 is just 2. And in our second case, a is 2. A is 2, so 2 times 2 is 4. This 2 times the denominator, you get 4. Now, so when you simplify this, you come to this. How do you simplify this? From this step to this step, we are using our Rust code. Our Rust code. So the Rust code, I'm asking you for the J invariant at this position. What about the J invariant at this other position? Then it's supposed to give me these values. It's supposed to give me 28, that, and this, the other one is supposed to give me 17, 28. So that's how you simplify using Rust code. You're not doing it manually at this point. So let me just share my Rust code for this. Okay, this is the Rust code. Now, this is the first bit. Where this is this is root I out of 2. Root I out of 2. And this is root I out of 4. So what is happening? What is happening is this. What you are seeing here is 2. So I just got the root of 16. The root of 16 is 4. then divided by 2, get this 2. But then I've said it's complex. I've told it's complex, so it knows that there's an I somewhere. I told it's complex, so it knows there's an I somewhere. And then this other one, 16 is 4. Divided by 4 gives you 1. So it is the one you're seeing here. It's the one you're seeing at this point. But then I've told it's complex so that it knows there's an I. It knows that it's I multiplied by root 16. Now, so I've asked it to give me 2 J invariants, one for this part and another one for at this point. So give me 2 J invariants. So it has given me the J invariants. The first one is 28, 74, 96. Another one is 17, 28. Those are the 2 J invariants. So those are the ones I now include in my calculations. So we got 17, 28 as one of them, and the other one we got 28, 74, 96. And remember, what I've gotten is the J invariant here. I subtracted from X. I subtracted from X, and this is what you get. And then I also subtracted the other one from X. You get this. You just subtract them from X. This is multiplication. I'm just taking this multiplied by this multiplication, because there were two sets. So I multiply J invariants to get the Hilbert space polynomial. So this is what we call the Hilbert space polynomial, the ones we have here. So the only thing we need to do is now to reduce these integers mod 13. Reduce these integers mod 13. When you reduce them mod 13, that's what I'm doing. This one mod 13 will give a remainder of 12. This one mod 13 gives a remainder of 1. So instead of this number, I'm writing 1. And instead of this number, I'm writing 12. This is now my Hilbert space polynomial, the reduced one. The reduced one. Now, so what do I do with this polynomial now? What do I do with this polynomial? What I do with this polynomial, I pick this value and this value, and I want to check whether I go to the cases. We had the case scenarios for the elliptic form, the elliptic curves that we can form when we get some J invariant. So when you get this J invariant, for instance, what are the possible elliptic curves? What about this one? What are the possible elliptic curves? But of course, I begin by disqualifying this point. I begin by disqualifying this point because this 12 cannot be J invariant for the curve we want. The curve we want earlier on, we had calculated the J invariant and we found it to be 1. So that means this is the correct one. The J invariant that is correct is 1, not 12. Because we had calculated this one earlier. And the J invariant for that curve is supposed to be 1 and not 12. So that's what I've just explained here. That's what I've explained. I've said from this we obtain J is 1 and J is 12. But this is not correct because we had done this one earlier and we found that the J invariant is supposed to be 1. Of course, you can prove that what we had done earlier is this. What we had done earlier when we were calculating the J invariant, when we began by J invariant. And we said to get the J invariant, you would take this 12 times 4. This is 4. This is A cubed. This is A cubed. And this is B squared. So for our case, our A is 8. Our A is 8 and our B is 2. No. Our B is 8 also for the curve that we are looking for. So I'm just proving that as, that 1 is the correct one and not 12. Because the formula for the J invariant, this is the formula. So when you multiply this, this is 8 cubed. When you reduce it, it will be 5 mod 13. This will also be 5 because it's 8 cubed mod 13, and this will be 12. So the numerator is 20 mod 13, that will be 7. And this one is also 20 mod 13, that will be 7. And this is just 12. Now, so the denominator now we have is 19. 19, and 19 mod 13 is just 6. 19 mod 13, this is 6. So this will go here 1, twice, and this is 14 mod 13. This will give you 1. So this is just proving that 1 is the correct J invariant, not 12. So when we reach there again, we drop the 12. We drop the 12 and only consider 1. Now, so when you go to the cases, we've seen that J is 1. So the only case we can now choose is J is not equal to 0 and J is not equal to this. This is the only case we can go for. This is the only case we can go for. We had those cases, we looked at them yesterday. There were cases when, for instance, a J would be 3. No, the J would be 0. There are cases when the J will be 0. And those cases when J will be 0, you would check whether D is -3 or whether D is not -3. So we had those. I'm just trying to remind you one of the cases we can consider. For a case, J is not 0. J is not 0, so we cannot consider this case. We cannot consider this case. So the only case we can consider is when J is not 0 and J is not 1728. This is the only case we can. And what are the possible curves here? What are the possible curves when J is not 0 and J is not 1728? The first curve that we saw under that category would be y square is x cubed plus 3c1 x plus 2c1. And the other one we saw in that category would be y square. Y square would be x cubed plus 3c1 c2 square, then plus 2c1 c2 cubed, c2 cubed, c2 cubed. So those are the two possibilities of it. So it says that this or this. So you try this one first of all and check its points. See whether it has the 20 points you're looking for. If it doesn't, proceed and check this and see whether it has the 20 points you're looking for. Now, since these are the scenarios, let us calculate C1. How do we calculate C1? Our formula that I gave was that C1 is supposed to be calculated by J naught out of 1728 mod Q, then you subtract J naught. Subtract J naught. Our J naught is 1. 1728 mod 13. Mod 13 will give you 12. 1728 mod 13 will give you 12. Then subtract J naught. Our J naught is 1. So this gives you C1 as 1 out of 11, which is just the inverse of 11 mod 13. The inverse of 11 mod 13. The inverse of 11 mod 13 is 6. The inverse of 11 mod 13 is 6 because 6 times 11 would be 1. 6 times 11 mod 13 would be 1 because that is 66. 66, 13 goes there 5 times because of 65. The remainder is 1. So it's 6. So C1 is 6 in our case. C1 is 6. Now, since C1 is 6, we consider the first equation and see whether we can get an equation that give us 20 points. Consider the first case. So the first case is this case. So it means y squared will be x cubed plus 3c1. C1 is 6 and plus 2c1. This is 18 mod 13. So this is y squared is x cubed. This is 18 mod 13. And this is 12 mod 13. So this is the equation we come up with. You check whether this equation has 20 points. If it has no 20 points, if it doesn't have 20 points, it means we go for the second option. Now, when I checked this using our Rust code, I found that it has 8 points. This equation has 8 points. So that means it's not the one we want. Since it's not the one we want, we now choose quadratic and recipe. Quadratic and recipe mod 13. What I mean is you choose a number mod 13 that has no square root. A number mod 13 that has no square root. At least you can use Rust code we had earlier. We had Rust code for doing this, for getting numbers that have square roots and those that do not. Let me just share that again as a reminder. I had just shared a code for doing quadratic residues. Quadratic residues those are numbers that have square roots, mod 13, but we want those that have no square roots. So the ones that have square roots mod 13 are 2, 3, 4, 5, 10, and 12. So this one have square roots. The one we want are those without square roots. So those without square roots, you can see 2 has no square root. It's not here. 5 is not, 5 is not here. 6 is not here. 7 and 8 are not here. Even 11 is not here. So those which are not here are quadratic non-residues. So we just pick any and multiply it by that curve, and then again try whether to see whether the curve has the number of points we have. If it does not have the points we have, we pick another quadratic non-residue. We have so many. You can see we have 2 is quadratic non-residue, 5 is another one, 6 is another one, 7, 8. So we have so many numbers to pick. So we pick one just at random and multiply by the curve and see whether the curve will now have the points we have, the points we want. If it does not, we proceed and pick another one, another quadratic and residue. Of course, at the end of it all, one of them would give you the points you want. One of them will give you the points you want. So I've chosen 5. 5 is one of them. Of course, I chose 2, and then I tried, it was not giving me. So then I decided to choose 5. So when you choose 5, you don't go at the start. You don't go at the start. You just multiply it by the first equation here. This equation that we gotten, remember this equation was giving us 8 points after putting in C1. Now you choose a quadratic residue, just choose C2 to be 5. You can try 2. It will not work. It will not give you 20 points. Now try 5. Now multiply this by 5. What is the equation? The equation is supposed to be y square is x cubed plus 3 C1 C2 square, then plus supposed to be 3 C1 C2 cubed. Now, but remember, we've already multiplied by C1. We've already multiplied by C1 to get this. This equation we've already multiplied by C1 to get this. So C1 and 3 are already taken care of. C1 and 3 have already been taken care of. Well, this is supposed to be 2. So C1 and 3 here have been taken care of. C1 and 2 already have been taken care of. So you only need to bring in now C2. So multiply here C2, and multiply here C2. And our C2 that we've chosen is 5. So this is what I'm referring to. So when you multiply this by 5 square, this will be 5 times 5 square, x, and this will be 12 times 5 cubed, x, supposed to be an x here. No, this is not x, this is a constant. This is a constant, but this one has x. Now, so just multiply that. 5, that is 5 times 5 times 5. And when you do that, this part, which is 5 times 25, reduce it mod 13, you get this 8. And this is 12 times 125. 12 times 125, there's no x. Reduce it mod 13, you get 5. Now try to see whether this equation has 20 points. When I tried, I found this one has 20 points. And again, we have a code for doing that. We have a code for doing that. Then after this, once you get one that has 20 points that you want, you do isomorphism. You map it to another curve. And that's what we did. And for you to map it, remember above, we've been using quadratic non-residue. And yeah, we went to that curve, that chord, and we saw that there were so many non-residues. And we said we would pick 2 and try, pick 5. So we chose on 5. Now, to map it, now choose a quadratic residue, mod 13. pick a quadratic residue, the ones we are seeing, those that have square roots. Call it D. Just pick one, call it D. And then you have your equation above multiplied by this square where there is A, and multiplied by D cubed where there is B. So the equation that we have is this. So multiply at this point, D cubed at this point. Because that is, so you just pick a quadratic residue, that have a square root. Now, so, you know, when I was doing this, I already had in my mind that I wanted a curve that has 8x, no, x cubed plus 8x plus 8. So I pick any quadratic residue, I multiply and see whether it gives me this. If it doesn't, I go to another one, quadratic residue. There are several of them. And then finally, when I reach that 12, multiply 12 by this and multiply here, where there is 8 multiplied by 12 square, and this 8 multiplied by 12 cubed. When I did that, finally, I ended up getting this equation. So you can see I'm just, where there's this 8, multiplied by 12 square, and this 5, multiplied by 12 cubed, and reducing mod 13. So when you do that, finally, you end up with this curve. But you see, you must first of all get a curve that has 20 points. Once you get a curve that has 20 points, now do this mapping. Do this mapping, and you're just multiplying it by D, a quadratic residue, mod 13. So you just use your code for getting quadratic residues and pick any quadratic residue there, multiply by your curve, and get another curve. So that is how you do it. If you wanted to get y square is x cubed plus 8x plus 8. This is how you then would have done it. But if you see, for this case, we had a specific equation we wanted. Now, if we did not have a specific, we did not have a specific equation, but we just wanted one that would give us 20 points. There are so many options. There are so many options. For instance, at the point where we were picking quadratic residue, like at this point, you see I picked 12 because I specifically wanted to get this equation. But if I would have picked anything else that is quadratic residue, I would have gotten another equation that has 20 points, but it would not have been this one. It would not have been this one, but it will still have had 20 points. Because at the start, we wanted one that has 20 points, and we also wanted it to be in a given field, mod 13. So that is what then we would have done. Now, so I'll then share this Rust code and the Rust. I've shown you how I'm getting the Jane variant. This is how I'm getting the Jane variant, and I said I'm not going to the details of getting this approximation of Jane variant. But you can use it, you can modify the code so that it can do everything that you want to do for you. Okay, thank you. I've also included the notes for how the code works. You can look at them. Thank you. Okay, Ken, you can You can stop recording, huh? Ken or Lynette?
Okay.
Okay.